who all went to the shindig. Congratulations on making it out of that building. I thought we'd actually reach a point. You ever read what was it, Dirk Gently's Holistic Detective Agency or whatever, where they get the couch stuck in the stairwell and they run all the computer simulations. They can't figure out how the couch got stuck in the stairwell. Like it never should have gotten there in the first place, and then they just cut the damn thing in half. I was worried we were going to hit that point last night at the bar. Like we get people in there and they just didn't physically have a way to get out, and we'd all just be like sitting there. Well, Shmoocon's starting this morning. We're all still stuck in the bar. But anyway, announcements and random things. We have the new parking passes for today, if you need said parking pass. We will be giving away and selling lots of swag because I don't actually think I have enough space to get it all back up to my house. So if you want like spare bags for your friends or enemies, depending on how you look at it, or any other odds and ends, you will likely be able to buy it in about an hour or so at the front desk. I think we're running really heinously low on t-shirts, but that's not what I care about because these red bags take a god-awful amount of. So please buy them for Christmas. It's a great time to get your Christmas shopping done. And they are six-pack coolers. I think there's been some confusion about, hey, these are neat soft-sided bags with bottoms that look insulated. They are insulated, and they are actually coolers. So they will be for sale. So anyway, I'm really excited about this talk, and I wish I could stick around, but unfortunately I have to go flee and get the registration system online. Hank and Clayton are going to be talking about a very interesting topic, why not to write your own crypto, and I think it's a fantastic title, so hopefully it goes well, and Clayton's got a shirt that'll wake you up this morning, so it's better than coffee. So anyway, I would say something about your lineage, but I'm not really sure where you came from, and I'd rather not say anything bad about you. So anyway, here you go. Yeah.
All right, so I'll try not to get too close and not to get too far from the microphone. First of all, so I'm Hank Leininger. Clayton Monroe is my co-presenter, and we're going to be talking not just about homegrown crypto, but about just basically, broken uses of ostensibly good crypto. Now, first of all, as he mentioned, congratulations everybody for getting here at 10 a.m. on a Sunday. This is the Shmoo after last night. So
I like the eyes on it.
What's that?
I like the eyes.
Yeah. So we understand that you have your choice of shows to sleep through this morning, and we appreciate that you've chosen ours to nap through. So okay, so the majority of this talk is going to be war stories. Things we looked at, what looked. Doing security assessments, penetration testing, application or device testing, and sometimes it looked like it presented as a hard problem, and then we realized, oh well, there's a shortcut, and there's almost always a shortcut, embarrassingly often, on the part of the vendors. So, as I said, go ahead.
And one other warning before we begin is Hank and my presentation style is core dump, so. Hopefully that won't be too bad.
Yeah, and the caveat: we're not crypto mathematicians. We're not crypto. This conference is filled with real crypto weenies. And yet we're able to break all kinds of things. And again, like I said, the bugs are often embarrassingly simple. We expect there's a whole other layer of damage waiting to be done. And you would think that a lot of these things we're going to point out, they're so obvious they should never have happened, but they keep happening, so it's worth it. And what kinds of stuff do we see? Well, the obvious is homegrown crypto algorithms, and that's almost always a recipe for disaster. But also occasions where, and by the way, that projector, projector seems to be a more stable image than that one. So I'm going to look over there because it's better in my field of vision, but I think if you have epilepsy, focus over there. Anyway, just frighteningly often, the keys for whatever gee-whiz, job of crypto implementation they've done are given away, like they're shipped on the CD-ROM, or they're in the beginning of the message that's the encrypted message or whatever. You'll see a bunch of those as we go on.
Or they're in a file, or
Yeah, they're hidden in plain sight in a file called password.dat.
Or in a routine called decrypt.
Yeah. So, and I love this quote, homegrown crypto is bad crypto. Every programmer tries to build their own encryption algorithm at some point. in one word, don't. And in general, security through vigorous hand-waving. Look, we use AES. Here's your key. No, that doesn't work. Go ahead. So again, we're not talking about breaking the AES algorithm or breaking SSL, but we are talking about breaking deployments or applications that are protected through otherwise and again ostensibly strong algorithms just used incredibly poorly to protect all kinds of things, encrypting data or generating session IDs or authentication, whatever. We see these things happen in all those cases. So now on to the fun stuff, the case studies. This is just a list of what they'll be. We'll walk through them. Go ahead.
In the interest of time,
Oh, yeah.
we may not be able to get to all of them, but we'll do our best. We may have to cut some short.
Yeah.
We'll take a
In
half
fact, it's almost guaranteed. This is a 2-hour talk that we cut to 75 minutes that we didn't cut to 60 and then added slides, which was maybe not such a good idea. So we'll see how far we get. I think the best stuff is the beginning. So for each one, we're going to talk about what's the situation, what's the application, what's it doing, why do we care, and then what did they do wrong, how did we discover what they did wrong. Maybe there were 4 avenues worth pursuing, but the first one we succeeded on, so that's it. We were done. And then, if possible, recommendations on what could have been done better. So our first one, oldie but a goodie, an online banking application, which, go ahead. Right before we tested this web app, it had been certified secure by one of those outfits that certifies websites as secure. A month before we'd been there. And we realized that various resources like images of checks that were, canceled checks, things like that. Nowadays, it's pretty common for banks to have like TIFF images or JPEGs of your scans of your checks. This was years ago, and it was not that common yet. They were doing that, great customer service, except that the check numbers were just, they were not protected by anything other than the obscurity of the file path. And the file path was generated based on your account number, encrypted in a super secret way. And the account number, by the way, was your Social Security number. Yeah. So go ahead. We realized, though, that the account numbers weren't encrypted. They were just obfuscated with a simple substitution cipher. And in this one, we just highlight some of the key tokens there. The letters basically correspond to the obfuscated account number. The number stream in the middle was the bank's routing number, so it's obvious it's not a secret. And of course, every example in here has been sanitized and stirred up and anonymized. But this is really the structure of the way the check files were protected.
And one thing to note right off the bat when we first saw it is, well, why were there ASCII strings surrounding this number in the middle, which was obviously not a secret? So that already was a tip-off in the beginning.
Mm-hmm. Then we could have taken a few more samples of valid accounts and valid check numbers and figured out, oh, this looks really simple. Maybe it's a simple substitution. But it turned out we didn't have to. There was a showcode vulnerability on the web server that allowed us to download this ASP code. Now, yeah. Again, remember, this is a place that had been certified a month before.
That doesn't even qualify for cache, does it? Decoder wheel?
Yeah, right. That would have been that's the kind of we have some other remind me later. So again, like I said, the account numbers were based on Social Security numbers. It was actually worse because this wasn't just a bank; this was a state credit union. And Social Security numbers are issued first of all with a prefix the prefix tells you what state it's in, and for any given state, there's only a handful of prefixes. With the batches that they're distributed in, pick your target age range for a state employee, maybe 30 to 50 or 40 to 60. And when you just decide to iterate through possible Social Security numbers in that range, I think we just sent requests for about 10,000 different, encoded SSNs and got over 1,000 hits, which we were surprised by, but not that surprised. And that was the entirety of the security of this application. It was part of a larger enterprise assessment. They had the website certified, but they had us do a general overall, I think, external pen test. I'm not even sure that it was a web app assessment per se. I think we just said, well, most of your interesting external presence is your website, so we're going to poke at the application, and we found this. So, go ahead. Okay, this one kind of hurts my head because I can't believe anybody would actually do this. So this was a really strange single sign-on architecture where it was basically different web servers that were provided by different vendors and didn't trust each other. There was no there was no credential handling server that then handed out tokens and whatnot. The sites used a shared secret key between each of the web servers. When you logged into one, it set some cookies that encrypted your credentials with that secret, and then that was set as a cookie that was sent to every other server in the domain. Don't ask me why they did this. And as we say there, the initial login page was SSL encrypted, but the rest of the application wasn't, because we're done with the sensitive stuff. Turns out we didn't actually have to do anything at all as far as breaking the crypto, because it turned out you could just submit an encrypted blob to a particular page. The login form had a remember my username feature, and anytime you viewed the login page, it would take the encrypted username cookie and decrypt it to populate the field and show you your username. Well, you could submit anything you wanted as the encrypted blob for the username, the encrypted blob for the password. So you get somebody's encrypted password cookie, submit that as an encrypted username, and the server gives you back the decrypted value. I'm done. So, and then we walk it through. Here you see one guy, when you submit a login request, and the remember password cookie is set to that alphanumeric, that hex string. And then you submit that as your remember username cookie, and what you get back is the encrypted password. So anybody's encrypted username and password cookies, you use those to get their password anytime you want. That, however, wasn't actually enough. I mean, other than the fact that it was embarrassingly bad, it didn't actually give us access to anybody's account unless we were able to steal their cookies. Since this is not SSL after the login, we could sniff it. But we didn't have to wait that long, because one of the many applications in this single sign-on site was a bulletin board. And that bulletin board had cross-site scripting vulnerabilities. So, 5 minutes of work to set up a malicious post to the bulletin board that, when viewed, would submit to us their encrypted cookie values. And once we receive those, we pass them in through the login interface as a remembered username to get the password out. One thing that's worth noting here is that this is a cross-site scripting vulnerability that leads to a total, like a permanent account compromise, not just temporarily hijacking a session, but actually getting the guy's permanent credentials and being able to log in as him at will and change the password. Well, why bother changing it? Just leave it. Again, we shook our heads. I still do. Go ahead. Then we have times where people think that good crypto is a substitute for business logic. And web services application that used SOAP XML messages, and they used the digital signature features in SOAP, which was pretty cool. So what that means is that you're talking over SSL, but inside the SSL message, the contents of your messages have themselves been digitally signed and or encrypted. And this is pretty cool. The server was configured to block or drop every message that came to it without a valid signature. So your standard web tools, just like, they have no idea. They can't do a thing to this. But we realized, and we were thinking, so okay, this is a Java client application, and when it launches, it does some interesting internal foo to generate a certificate and uses that certificate for the remainder or private, public-private key pair. And we thought, all right, what we're going to have to do is disassemble this Java app or put it under debugger, watch it go. Once it's generated its key pair, or once it's pulled it out of its magic hat, we're going to just snarf it out of memory and then use that. It was way, way, way easier than that. So here's an example of a valid signed request, and I've edited out most of the bits except for the bottom. The signature value, and it's a base64 encoded string. It's a public key signature. Go ahead. If you tamper with the message at all and submit it, the server responds with blah 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 blah. The signature verification failed. So that's what we're saying. We can't just tamper with messages and submit any values we want. And that's where we're thinking we're going to have to get the client's key and build these ourselves. But no, we don't. Go ahead. It turns out, so again, this is a SOAP application that's a fat client. The business logic is not purely on the server side. The client is doing interesting work. So in one case, for instance, the server would pass to the client a list of valid options of, do you want to log in as a user or do you want to log in as an administrator? And normally, the list would only come to the client saying, do you want to log in as administrator? And the client would say, yes, I want to log in as administrator. But we realized just by simply man-in-the-middling, Stunnel and a SSL or a little Perl proxy, we could inject messages to the client that said, I want to be an administrator. Or, I'm sorry, that said, do you want to be an administrator? And the client would say, yes, please. And the client does all of its, goo to build a properly formatted, digitally signed message, and we submit that back to the server, and the server takes it. Go ahead. So, like I said, the server had no server side. There was no business logic in the server that made sure. Wait a minute, this guy's logged in as user 123. Is user 123 really an admin? It didn't bother checking. It figured, hey, the signature is good, the crypto is all kinds of good. We're happy. Sure, what do you want to do? So, obviously, the solution here is actually putting in some business logic on the back end to verify. One thing that could have helped is having the client verify that the messages from the server are signed. That would have meant that this easy route wouldn't have worked, but we still could have. The client is still in our possession. We're running it on our own box. There's no way you're going to keep somebody from getting the matter of how long, how hard you want to make them work. So there's no substitute for the business logic. But even the pure crypto angle, they could have done a little better.
And this is something that other examples that we'll get to down the road here, a lot of them where you have a thin or a fat client on the client side, and the server is doing too much to trust that client. Mm-hmm. So we have other examples of first like that.
Yeah. And I like that one because XML, SOAP, blah, 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 it's the latest pile of buzzwords and web services stuff. Sure.
Just to clarify, in that case, the way that you were able to get that digitally signed message was you set up a proxy that the client thought was the server.
Yeah, exactly.
You didn't do any verification with the other certificates, SSL certificates.
I actually don't remember if the client was initially verifying the server certs. It wasn't. Or that was easier to circumvent than extracting the private key from memory in the client, because we were pursuing it on several fronts at once, and we might have, by that time, already subverted the key store that it was using. Because, again, we could have, let's say, put our own public key or server certificate in the key store of the client, and then when the client fired up, it would have trusted our thing. That is a very good roadblock to put in. It's a good speed bump to throw in somebody's way in a client app. To force, although there is a case later on in this where specifically wanting to make sure that the client knows the server certificate actually gets an application in trouble. So.
Right. It's interesting because in that case, we'll get to it, but the client did verify the server certificate, but we could just turn that part of it off. We'll get to that.
Oh, you're thinking Okay, so yeah, there's multiples of that.
There's multiples, I guess,
Yeah.
all right.
So, okay, now, we have a case of enterprise security management software. Go ahead. I'm not going to be too specific about what this enterprise security management software is or does, but it is a enterprise security management software. There's a server piece that manages devices, rules, and report logs. I don't know what kind of rules, I don't know what kind of logs. And there's a client piece. There's actually two clients. There's a fat GUI Java client for configuration management, and there's a simple SSL web interface for just viewing event records. And well, everything's encrypted. The server to, maybe it's the next slide. Yeah, the server to end node device communication is encrypted with an AES implementation. The keys, the secrets to use for that are configured in the GUI in the management interface. And my beef number one is that the GUI only allows you to enter alphanumeric keys. It's kind of dumb for a security product to artificially limit your key space. Oh, and it also doesn't enforce a minimum length, so you can use a password of A. And we noticed that the initial, the beginning of every communication over this AES channel started out exactly the same way for at least 1 or 2 blocks worth of data. So we thought, maybe there's no, maybe there's no feedback. Maybe they're using ECB mode instead of CBC. So maybe we can do a dictionary attack because we know users are going to be choosing their passwords, and we know that their passwords are going to be only alphanumeric. But again, maybe there's an easier way. And it turns out there was. We looked at the client-server part for the management interface, and it's using SSL. Great. And when you first fire this up on it with a browser, it says, hey, this server you're pointing to has a certificate that's registered to so-and-so incorporated. Do you want to accept this certificate? And you say, okay, sure, I just deployed the box. Deploy another box just like it later, and you don't get a warning. And if you think about it, it's because the server certificate came on the install CD. The server's private key came on the install CD. The server's private key came on every install CD ever shipped to any customer anywhere in the world. And actually, you don't need the CD because you can download the software. Oops. So, I mean, there's a couple of hoops. Go ahead to the next, yeah. So it's not just sitting there waiting for you. It's in a Java key store file, and that file is encrypted. But since the server be able to decrypt the file, guess what's sitting in the same directory? A properties file with the password to decrypt the key store. So take that out, do a little dance, and now you can SSL dump, or you can impersonate the server yourself, capture somebody logging in, get the administrator's credentials logging in either through the web interface or through the Java GUI. Either way, it's the same credentials, username and password, that then you can use to log into any component in their infrastructure, and change the policy any way you want. Add rules that allow yourself or ignore you or whatever this thing happens to do. And actually, this was one of the first cases where I'd really looked into this and confirmed that it works. But I come to think of it, I think I've seen a number of other packages that behave this way, where I'm pretty sure the server certificate is, like I said, bundled with the software. It just comes out of the box, and there's no generate your new certificate installation kind of process. Sure.
So this is a very common because customers, a lot of RFPs say, yes, all right, so you have to be able to do HTTPS out of the box, and the vendor has a couple options. You can buy a valid trusted certificate, not recommending that, that's what these guys did, right? You can have a feature to generate your own certificate, which will then not be trusted, and then we're advocating the just click OK mentality for getting by SSL certificates. Or you could just, have an HTTP by default, and then you have to take extra steps to try HTTPS.
Yeah.
So, speaking from a vendor perspective, this is a very common problem, and there is no easy solution here that will be acceptable for a lot of customers. This is part of the reason why SSL sucks.
Yeah. For the sake of the recording, the question or comment was, this is a hard problem for vendors. Absolutely, because and you mentioned, what are your choices? Your choices are HTTPS only. Somebody want to turn down their Kismet? That was a little loud. So you could ship HTTP only by default, which is going to get you spanked by guys like us. You can ship a canned certificate like this, or buy one and ship it, and then you'll get spanked by guys like us. Or you can generate your own certificate at install time and get users to hate you, because then they're going to deploy this stuff and they're going to have warnings everywhere. I would still prefer, obviously, the high security option. Making it brain dead obvious. Here's how you distribute the certificate that we signed this with, or whatever. Deploy this to all your browsers. Tell all your browsers to trust this, and then they won't complain. And usually that can be done with I'm not a Windows guy, but probably a login script or whatever.
It is a trivial problem. If you're installing software, you can install a damn certificate at the same time.
Yeah. Well, the difference being you might have to deploy the certificate to like hundreds of people as opposed to just deploying. But you should have a process, that handles that, and then you just drop it in.
You can install the certificate at the same time. We have done this where I work, and I do not work in a whoop-de-doo high-tech environment. This is a trivial problem.
I think it should be. Well, another thing you could do is simply have a trusted place where you publish the checksums of the homegrown certificates that you've deployed. So there's an intranet website that's SSL'd that people know to go look at, a page of, if I get a pop, I don't want to just click OK. I want to read the fingerprint and compare it. Now, I'm not going to talk about the logistics of getting regular users to do that, correctly.
This is such a common problem, though, so everybody in this room should think about the appliances they log into and how they're actually doing private key validation, like your routers, your black boxes. Everybody has this problem, and this is like overlooked all the time. And I'm sure half the people in this room have this problem and don't know about it.
Yeah, I agree.
Considering that you get certificate authorities free and sign your own certificates, deploy that internally for your infrastructure, and considering on a relative basis how low cost it is to get service certificates signed by a legitimate CA for public-facing certificates, it's a no-brainer. Do it right.
Yeah. Yeah.
Use a PKI, damn it.
Amen.
Yeah.
Don't give me better excuses as to why it's so hard. Educate your customers as to why it's so smart.
I mean, my complaint again is that if you don't do that, it's snake oil. It's vigorous hand waving. Look, we have SSL, and here's your key. So, it's not a trivial problem, but it's not impossible either. Go ahead. Okay, so now we have this is another like enterprise management tool. In this case, it's go ahead. It's a network management device where basically a network management company wants to provide an outsourced service where rather than having to have engineers on site, they can tell you remotely what's wrong with your network. You get a box shipped from them. You deploy it in your network. You teach it how to manage all of your box, how to SNMP poll or give it the Telnet SSH whatever credentials to get into everything in your universe, and it harvests all that data, most of it just health and performance kind of stuff, and uploads it to the mothership, the back end, over the internet. And when we looked at this, they said, "Oh well, the communications they're triple DES encrypted," and we said, "Oh okay, we're gonna validate that." And I mean, good for them to ask us to look at it, right? But I don't want to tell you how many years this thing had been in service before they did have. Well, maybe they'd had other people look at it before us, but it had been in service years before they had us look at it, and we found that the triple DES keys were being given away. Now, the way we typically do like appliance testing is we take a black box approach, and I think R.A. Rubin Friday said that one of his stages would be taking the box apart. That's the first thing we do actually is if it has screws, I'm going to unscrew them. If it has a hard drive, I'm going to take it out and I'm going to image it. I might not, if it's flash based or something, if I don't have the stuff handy, that might not happen right away. But a hard drive, absolutely. I'm not even going to turn the thing on before I've ripped the hard drive out and imaged it and put the copy back in. And we used a tool, F-Times, that Clayton wrote actually, to map system, gather all the timestamps, MD5 sum everything, and right away we could bash that against reference libraries that he's created of and some that are publicly available of checksums for known binaries shipped by Sun or by whomever, and isolate out the code that's that they've touched, stuff that's new, and we also did packet captures of, we went ahead and let it do its thing. We set up a little dummy network and gave it a 2600 to manage, and it said, "Gee, I don't have any links up." I said, "That's nice," and it uploaded its data to the mothership, and it was FTPing not binary goo but ASCII encoded goo, and all right, that doesn't look like a tarball, but since we have the box and we have the file system sitting in my home directory, I looked around at, we found the code that gathered up, and basically we worked backwards from the cron job to figure out how is this thing actually bundling this stuff up. And we found the tools that did the encryption, and they were being called with some parameter, and we said, well, that's the key, but where is the key? So we kept going backwards till we found how the key had been generated. And then we went forwards to see where the key went. Like, what did it do besides, when you called that one tool with it as a parameter, what happened? And then we saw that when the payload was built, the key was part of the payload. Here's a capture of an SSL, or actually this wasn't even SSL because it was encrypted already. So an HTTP post of upload to their server, and the first few lines, that first bit looks an awful lot like a file name, and then we have a short alphanumeric string, and then we have a very long, but I mean 100 and something character wide third line, and then consistently 70-ish characters wide the rest of the payload body. Not UU encode, not base64, but something along those lines. Clearly an ASCII, encoding of binary stuff. So, and then an FTP looked very similar. Have the first header line of the file name, but that's what was stored. It was stored as that file name. So that kind of confirmed that the first line in the HTTP post was the file name. And again, the same kind of first line, and then the same long second line, and then the consistent pile of goo content. And so again, we looked around and we found their ASCII encoder. We said, oh, okay, this Solaris binary, you feed it a sequence of bytes and it spits out a sequence of ASCII. And so we made ourselves a little character map that translated back and forth, wrote a Perl script that implemented it backwards and forwards. So we could now encode or decode. I mean, it was some really obscure file name. Their tool was called like charmap. So that was the encoding scheme. But is that really all there was to it? I mean, do we now have the contents of the tarball? Actually, but we can decode it. Once we decode it, we see the header lines, again, the file name. And then that next bit, let's see, that's probably a checksum and a file size. And then one line where it's KLS TST serve, that was the name of our test device. Oh, we know that. A numeric sequence which mimics what's in the file name. That's interesting. And then transport vault.tar. Well, that's probably the name of the thing that just got bundled up. And Outback server was the name of their, back-end server. So yeah, here we've extracted and decoded the lines. And actually, did you skip one? Okay, yeah, that was where we were. So go ahead. So again, we decode that, and then now the rest of the stuff after that one long line was the consistently 70-ish character. So we dumped that out, and it's the encrypted tarball at that point. Go ahead. And we realized that the encryption they were using was just the plain old-fashioned DES tool out of like the libdes version 4, from back in like the mid-90s or something, early 90s, I think. And the key they would generate, also using their encoder. The key for the triple DES encryption was that prefix of the transaction. We called it a transaction number, and eventually later they confirmed that's basically what they called it. So the transaction number, the transaction ID, and the host name are the two things that get stirred together to make the key. They don't get stirred, actually. In fact, they get truncated. The host name is ostensibly part of the key, but it's really not, because the key ends before you get to the host name. So all you need is that transaction number, which is in the file name, which is the first line of the transaction. So put it all together, and so we've extracted the encrypted payload, and we just call DES using the encoded version of the transaction number, and we get out of it a tarball, and then we unpack the tarball. Yay! And yes, it does have device credentials. It has everything about the back-end enterprise. Everything you need to manage, which is to say, completely destroy the network infrastructure of a managed company. This wasn't a small mom-and-pop, managed service. This was a huge vendor providing the service this way. To their credit, they actually go ahead, keep going. I don't remember if we. No, okay. So that just kind of sums it all up. To their credit, we told them about this in maybe June of some year in the past, and by August they had a revised version that used HTTPS and GPG, and I've never seen a big company move that fast, so I was really impressed. How long it took them to deploy the patch in the new version to every single customer, I have no idea. That might be another story. So. And that had, again, like I said, it had been out there for I don't know how long. Just nobody looked at it, as far as they knew. Yeah. Okay, go ahead.
Okay, Hank, get to take a little break.
Yes, excellent.
This next one.
Oh, sorry.
Gee, I didn't know you liked me. This next one, convergent technologies, both Hank and I were like, what the heck is that? And it just turns out to be a buzzword that big companies like to create. And it was really just an application that sat on a device that brought together things like calendar, email, messaging, voice. And it was... they had clients for both Windows x86 and CE. And it was a mixture of web-based and proprietary communications. And we like this one because they have both kinds, AES and XOR. And both turned out to have problems. Because this was a fat client and it was Windows-based, we decided, hey, let's just go ahead and take a look at these binaries. So put them in some disassemblers, and you see things like encrypt and decrypt in the export table or the import table, depending on where you're looking. And after just doing some basic F-time string search type stuff, we come up with a key that you can see up there in red. And so I'm like, well, that looks like a key. It's 16 bytes long, so let's see where we can go. Later on, we created a dig string pattern out of that and searched all the files in the FAT application to see if there were other keys as well. That didn't turn anything up in this case. But one thing that was a flag to me right away on it was that the fact that their key was 0, 1, all the way up to F. It looked to me like they had, I don't know if purposely, but they had chosen a key that was basically hex. ASCII hex. So to me that limited the key space right away, and this shows you the difference just by choosing ASCII hex versus any number, because this was a DLL. This was a string initialized in a DLL. It could have been the full key space, but it wasn't. So why did they choose that? It wasn't like some user had to enter it in. So 64 to the 64 is still pretty big. I can't crack it, but that doesn't mean other people can't. And but was it really something that we needed to consider? We were looking at this and saying, there's probably more shortcuts or implementation issues here. So let's keep looking. One plan that we had initially is to take this recovery key and go find, one of those AES implementations out there.
We use the one from OpenSSL or something.
Yeah.
Just plug our own in, basically.
Right. And try to mimic the encryption and decryption of what was happening. But then, these encrypt, decrypt routines look so enticing that we're like, we got to have some fun. So we decided to write a tool in C or something to interface those encrypt and decrypt routines. And we had to do a little disassembly to do that. But one of the things that was nice about that is it eliminated some potential gotchas for us doing the testing, because if we had just gone out and pulled any AES implementation out there, it may or may not have produced the same results. Like, they may have tweaked their version of it just slightly. And so we could have been spinning our wheels for hours and hours.
In other words, their implementation might have been buggy, and if we hadn't used their same buggy version, our results wouldn't have matched theirs.
Right. So this snippet here just shows you, basically, this is the sum total of work required to go ahead and leverage the encrypt and decrypt routines that were in the DLL provided with the FAT client. And the stuff in red, we just took the key, we poke it in, and we go ahead and use load library to load in the DLL and then get proc address. And whatever data we want to encrypt or decrypt, we just go ahead and call routine. So that gave us the ability to look at, like, if we saw a file that had high entropy in the file system, we're like, that's probably encrypted. Let's see if we can decrypt it with this. And we got results. There was a user profile that we were able to decrypt, and inside there were other interesting things. It also allowed us to custom messages. And it revealed a new problem, which was, it looked to us like they were using ECB, electronic code book, instead of like anything that had feedback, like cipher block chaining. And the reason it wasn't a good choice, this is an example of the blue is the encrypted. There's some gray X's in there. Of course, that was stuff we had to sanitize. But the yellow is the decrypted counterpart. And the first thing that we did was we said, well, let's change one byte. And you see up there in the top left-hand corner, the C5 has now been changed to C4. It's in red. And the result of that was the whole 16 bytes on the decrypted side had changed. So that told us right away, block cipher. Because at that point, I don't know if we really knew it was AES yet or not. We knew there were, we could leverage these encrypt routines, but we were still trying to feel our way through it. Then if I changed the entire first row of 16 bytes of data, only the first row of the plain text was affected. More evidence to that point. And
I think more importantly there, until there's no MIC associated with the cipher.
there's
Yeah.
no what?
There's no MIC associated with the cipher.
Yeah, and so one of the things that we realized is that if there was ever a block-aligned bit of data that we wanted to change, we could just poke one block out and replace it with, in either direction, replace it with our chosen plain text and have it be, a valid encrypted message, or vice versa. Poke one spot out of an encrypted message and have it pop out to be our chosen plain text result.
Right, and one example is, if you look down at the bottom where you see the ID tags, this is XML, so, XML, it's much harder to go in and fiddle with it because it's self-correcting or self-checking. But there were cases where if the ID was just the right length, it would fall on a 16-byte boundary. And so we could, in certain cases in the XML schema, poke in data that would actually pass through. And so in that case, you wouldn't have to do any encrypt and decrypt. You could target the sections of the ciphertext. And so then this is just a repeat of the data that we had, put in to do the test. And you can see that the output is the same. So the other thing that became interesting to us on this was that the DLL was deployed both in the client and server. So, we were tasked to look at the client application, not so much the server, but this was very interesting to us because it meant that if we had set DLLs a lot harder and looked at them, with a really fine-tooth comb. Something that an attacker could do if they chose, at their leisure, over a long period of time, they may be able to come up with something that could attack the server and would be effective. Okay, now the other problem, which we'll just kind of do real quick, is XOR. They put the user credentials in the registry, and all they did was obscure them with XOR. And it seems silly to us for them to do it, but they did. So.
And if I remember correctly, the registry keys weren't protected. They didn't have ACLs on the registry keys.
Right.
So anybody who had access to the box could just pop them out. No hacking required.
Exactly. Okay, so now another one. This is the one that I was referring to earlier, where you have an SSL protected, and the client application, which was on a mobile device, was actually validating the server-side certificate. And so, we were like, what the heck are we going to do? And it turns out this was a brew application, and the fact that the encryption was there and the client-side checking of the certificate was there, supporting our desire to do man-in-the-middle or any kind of that. And but we were given this handset in test mode. Now, test mode is not something that you normally get on a device.
The brew architecture has some good hardenings designed in that are essentially, unless the phone is in test mode, you're not supposed to be able to tamper with various bits on it. The application is supposed to be signed and their data files and whatnot. So you shouldn't be able to do the manipulations we did. We did it this time because we had the phone in test mode for testing. As I think we mentioned in a later slide, though, during this engagement, we also found copies of the flash images and the tools necessary to flash them onto the phones you buy from the store and go flash it yourself, and/or put the phone in test mode yourself. That was just a single case in point of a single model of phone, but it's gonna happen. It's the nature of the beast. So assuming that a phone is never going to be in test mode is not enough, security model.
Right, and our own experience in testing the devices bore out the fact that if you try to tamper with one of these applications and the phone is not in test mode, then it's not going to work because the application is digitally signed. But we like to, when we attack stuff, we like to kind of pull back everything and remove all the assumptions. Say, well, what if you could do this? What would the result be then? So, the fact that we know the protection layer is there, but we don't concern ourselves about it because we want to know what happens if that gate breaks. What else is left to defend the castle, so to speak. And so we said, suppose that you could bypass this. Now, brew is not at the native layer in the phone. It's one level up. It's kind of like a Win32. There is a chance. We don't know how to do it yet, but that you could get underneath this, and suppose you could just replace the Qualcomm certificates.
And some things can, and again, it's an arms race. Some applications are designed so that when an existing phone switches into test mode, the application destroys itself. Now, how well does it destroy itself? Can you read the raw blocks off the device and reconstruct the files? Maybe. But again, if you have the flash image off a CD, you don't really need that, do you?
Okay, so because it was in test mode, we looked at this binary and basically, did some string stuff, basic, disassembly type things, and we found that there was an array that a two-length array, HTTP, HTTPS, and basically what we wanted to do was flip-flop. We knew that it was automatically going to HTTPS, and that was the first item in the array, so we just flipped it.
And fortunately, there was a bit of padding. There was an extra null at the end of HTTP, so you could poke the S in.
All we had to do was just null out the S and put the S on the other one, and by doing that, when the application came up, it now spoke just regular HTTP. Well, that solved our whole man-in-the-middle problem with the client being able to verify the certificate, because that was no longer done. And the thing I think it was most surprising about that is that the server side, the server applications allowed this to happen.
Yeah, there was nothing on the server that said, hey, wait, you're posting to a form that's only supposed to be accessible by HTTPS. What are you thinking? I'm going to deny you. Of course, we could probably have SSL man in the middle, you know, put a funnel back and go in the other direction to feed the stuff to the server over SSL, but then the server should have been using a valid client cert. Again, that's a speed bump that should have been there and wasn't.
Yeah, I think so. So you know, the server applications, the willingness on the server's part to talk both was a big issue, and I think the other issue here is that just because you put a protection in, like in this case, we cheated, right? We knew the phone was in test mode, so that we could actually do something that you couldn't normally do. But the other belief, you know, the belief that, you know, because you have a protection mechanism in place, that it's going to work 100% of the time. I think that's something that people have to get away from.
So this is just stuff that we just said that, you know, why is the server even supporting HTTP? Why isn't it exclusively supporting HTTPS? Or maybe specific functions that you know are sensitive, if you have a mix of them, those functions ought to check, hey, wait, am I running under SSL? And if I'm not, you know.
Okay, here's another case
Yeah.
that we had. We're running, it's 1052.
Maybe make this our last example, because it's a good one. I don't want to miss it.
Okay, this one here was another FAT client, and it did some database stuff, and the client needed to make queries to the server to get certain bits of information. The database traffic was not encrypted, but the fields in the database were. Unfortunately, this thing used hard-coded keys and weak obfuscation techniques, and it leaked credentials. And it had, you know, unique credentials for different things. They had tried to compartmentalize, because this was a manufacturing application that stored secret recipes to different products. And those recipes, only certain people in the company were supposed to be able to access certain parts of a recipe. So the procedure kind of went like this. There was an application, and you would run it. And then you would get up a dialog, and you would go ahead and put your username and password in there. And then it would, internally inside this executable, it would create a query. It had stored database credentials, so it used different credentials to talk to the database, but those were stored in the binary too, and we saw those too. But what we were after at this point were these user and credentials. And so it made a to the server. It looked something like that. It wanted back these four things. There's really no significance to the sum key 22. It was just, you know, some field that, you know, some key. So then what happened was the U1 field was checked until they found a match for the user 123. And then this is happening in the client now. The query has gone out to the server. The response has come back. These fields are encrypted. Then you look for the U2 and you see if the encrypted value matches what the user supplied, hammer. If the both checks pass, then you go ahead and decrypt U3 and U4, which is that user's credentials to get into the database. And then at that point, they're good to go. Well, all of those were done locally. So, you know, we had full access to the binary. We could sit there and run it in Ollie debug, and we could just wait for all this to unfold. We could sniff the results going from the client to the server, so we could use that to help, you know, decipher what was happening. And we also used Ollie debug, and one of the things that we saw when we were doing this is that the executable code, you know, it would open a file and it would parse it. And this file was 1,536 bytes. I'm like, that's a pretty big key, because when I looked at the file, it looked random. But after some, you know, analysis, we determined that, hey, this key is not really 1,536, it's only 57. So why is the file so big? And this is where the obfuscation techniques had come in. This is a screenshot of Ollie where we actually had isolated the key after pulled out of the file in memory. And it turns out that this was the essence of their obfuscation. We reversed it from the assembly, and then we wrote C code to do it ourselves, so that way we could just pull out the key from the file at will. And the key points here are in red. There was an initial offset, so that was like the super secret starting point. And if you get to that point, then you take 1 byte every 7 bytes, then you put those, you've got yourself a key. And that was the sum total of that. Now, because multiple records were returned, we were able to decrypt other users' records. And in fact, we could go into the SQL, instead of selecting a particular set of fields, we could do select star and select all records. And we also wrote a program to abuse the DLL routines that were exported, and you saw that earlier in a different example. So sure, we took the data, and that was okay.
Okay, well, we did make it through. Well, we cut 1 or 2 out before we started this morning, so when the full slide set goes up somewhere, there's 1 or 2 more. I think we only have about a minute. If you want to, can you make it through the pre-hash stuff in a minute?
Okay, pre-hash, basically, hopefully everybody is familiar with how session IDs are put together. Usually you have some combination of things like username, IP address, a nonce, a time. These things are smashed together and hashed, and that's usually how a session ID is created. Well, one of the problems that you get to is if you smash them together in the wrong way, you can be weakening your session ID. And this is the example. If you have fixed data at the beginning of your, the stuff that you're smashing together before you hash it, then that fixed information can be pre-hashed and stored, and so you can create you can get faster crack times if you're able to crack the variable. And here's an example. I have the stuff documented here at that link at our CoreLogic site. But here's really the bottom line. The red line going across the top is just every time you concatenate the fields and you hash them, that's just doing 1,000,000 computations of computing this hash. But if you take our shortcut method, you actually, the longer the string gets, the faster, the more easily the less time it takes, I should say, to go through that 1,000,000 tries. Thank you.
So you want to just skip to the very end? Yeah. So and we summarize all of the records that we've been making all along. Keep going just to the. Yeah. Just go ahead to the very last. Yeah, that one's fine. So. Extra credit question, if you guys find us and know the answer, I don't know what we'll do. I'll write a book and give it to you.
Thank you.
Thanks, everybody. Since I think we ran long, we don't have time for questions. You can come find us around. We'll be here for the rest of the day.
Who's next? I don't actually know. I haven't looked at the schedule. Is it Major? Oh. Does anyone see? Oh, there's Major. Hey! You look at all bright-eyed and bushy-tailed. Someone just made the comment that we may be injuring the security community by giving out too much free beer and killing too many brain cells. So.